In this lecture, we will discuss the pH scale as a measure of acid or base concentration. In this video, we will introduce the concept of the pH scale. Additionally, we will calculate the pH of a solution from the known concentration of H3O+, or hydroxide ion. And lastly, we will investigate the relationship between the pH scale and the pOH scale. In previous videos, we have seen that the acidity or basicity of a solution is greatly dependent on the concentration of hydronium ion in the solution. One of the most important methods for measuring the concentration of hydronium ion is by using an electrode that detects the ion. Two important ideas come into play at this point. First, the concentration of hydronium ion in solution is usually very small, typically on the order of 10 to the negative 3 to 10 to the negative 6 molar. Secondly, electrodes respond logarithmically to the concentration of hydronium ion. It is for these reasons that we commonly use the pH scale as a measure of the relative concentration of hydronium ion in solution. The pH is defined to approximately be the negative base 10 logarithm of the concentration of hydronium ion. This is the same approximation we use when writing a Kc expression. By definition, pH is equal to negative log of hydronium ion concentration. We will introduce other p scales later in the chapter, but they all start from the same idea. When we see this lowercase p, it means that you take the negative base 10 logarithm of whatever follows. For example, we will discuss the pOH later in this lecture. By definition, since hydroxide ion follows the lowercase p, pOH is defined to be the negative base 10 log of the hydroxide ion concentration. When discussing the pH, the natural starting point is pure water. As we saw in the last video, pure water is considered to be neutral at 25 degrees Celsius, and this is because it has equal concentrations of both hydronium and hydroxide ions. In this case, the concentration of each of these is equal to 1.0 times 10 to the negative 7 molar. So let's go ahead and calculate the pH of pure water. As we saw, the pH is equal to the negative log of the hydronium ion concentration, or in this case, the negative log of 1.0 times 10 to the negative 7. This gives a pH value of 7.00. Thus, we see that the pH of neutral pure water is 7. This will be our reference point when defining whether a solution is acidic or basic based on pH. As with any other calculation, we need to maintain the proper number of significant figures when dealing with logarithms and exponentials. It turns out these rules are actually quite simple. First, when taking a logarithm, the number of significant figures in the argument of the logarithm determines the number of decimal places in the logarithm. Conversely, when taking an exponential, the number of decimal places in the exponent determines the number of significant figures in the exponential. Let's work an example. We will calculate the following values and report to the correct number of significant figures. First, we will look at the base 10 logarithm of 0.002051. Secondly, we will look at the natural logarithm of 1.05 times 10 to the negative 4. In our first case, the log base 10 of 0.002051 is equal to negative 2.6880. Notice that the argument of the logarithm has 4 significant digits, 2051. This means that our value of the logarithm has 4 decimal places. Secondly, we take the natural log of 1.05 times 10 to the negative 4. This is equal to negative 9.162. Once again, we see that our argument of the logarithm has 3 significant figures in this case, 1, 0, and 5, causing us to have 3 decimal places in our logarithm value. Now let's look at an example involving exponentials. Please be aware that the base of the exponential is not important. The rules are the same regardless. In our first case, we will take the base e and raise it to the negative 2.58 power. In the second case, we will take the base 5 and raise it to the 0.1005 power. For the first value, e to the negative 2.58, notice that we have 2 decimal places in our exponent. This means that our exponential value, 7.6 times 10 to the negative 2, has 2 significant figures. Next, when we raise 5 to the 0.1005 power, we have 4 decimal places in our exponent. This means that our result, 1.176, will have 4 significant figures. Let's return to the pH scale. First, we're going to consider an acidic solution. Recall that an acidic solution is one in which the hydronium ion concentration is greater than 1 times 10 to the negative 7 molar. What is the pH of a solution that has a hydronium ion concentration equal to 2.5 times 10 to the negative 4 molar? We begin with our definition of pH, and we find that we have the negative log of 2.5 times 10 to the negative 4 molar, which is 3.60. This demonstrates that our acidic solution has a pH below a neutral pH of 7.00. In fact, at 25 degrees Celsius, this will always be true. Any acidic solution has pH less than 7. What about a basic solution? Well, recall that a basic solution is one in which the hydronium ion concentration is less than 1 times 10 to the negative 7 molar. So let's find the pH of a solution that has a hydronium ion concentration equal to 5.4 times 10 to the negative 10 molar. As before, we start with our definition of pH, which in this case is negative log of 5.4 times 10 to the negative 10. The pH value turns out to be 9.27. In this case, we see that our basic solution has a pH above a neutral pH of 7.00. And again, at 25 degrees Celsius, this will always be true. Any basic solution has a pH greater than 7. Before moving on, we need to spend a moment to clarify a common misconception. Unfortunately, many students are taught that the pH scale is limited to being between 0 and 14. This is not true. For example, consider a solution that has a hydronium ion concentration equal to 2.0 molar. The pH of this solution is negative log of 2.0, which is negative 0.30. So clearly, if we have a very concentrated acid solution, we will have a negative pH. Likewise, a very concentrated base solution, for example with a hydroxide ion equal to 3.0 molar, will have a pH greater than 14. Now, it is important to remember that when making pH measurements lower than about 2.5 or higher than about 11, we will generate significant error in our readings. We rarely work with solutions that are this concentrated, but we are certainly not limited in possible pH values. To this point, we have only considered the hydronium ion concentration, but we know that we can define a solution in terms of hydroxide ion concentration as well. For example, suppose we have a solution with a hydroxide ion concentration of 1.2 times 10 to the negative 3 molar. Recall that this is a basic solution because our hydroxide ion concentration is greater than 1 times 10 to the negative 7 molar. How do we go about calculating the pH in this case? Well, there are 2 methods. The first method is to calculate the hydronium ion concentration using the Kw expression and then using the definition of pH. We begin by rewriting our Kw expression so that the hydronium ion concentration is equal to Kw divided by the hydroxide ion concentration. We can then substitute in our values, in this case 1.0 times 10 to the negative 4 for Kw, and 1.2 times 10 to the negative 3 for our hydroxide ion concentration. When we do this calculation, we find that the hydronium ion concentration in this solution is equal to 8.3 times 10 to the negative 12. Having found the hydronium ion concentration for the solution, we can now calculate the pH directly. The pH, as before, is equal to the negative log of the hydronium ion concentration. which is equal in this case to negative log of 8.3 times 10 to the negative 12, which gives a pH value of 11.08. We can simplify this process by introducing what's known as the pOH scale. First, we'll take a look at how pOH works, and then we can investigate the relationship between pOH and pH. By definition, pOH is equal to the negative base 10 logarithm of the hydroxide ion concentration. Recall that the hydroxide ion concentration decreases as the hydronium ion concentration increases, and vice versa. The pOH scale behaves the opposite to the pH scale because of this reason. Let's begin by considering an acidic solution. In this case, a solution where the hydroxide ion concentration is 2.8 times 10 to the negative 9 molar. Again, by definition, pOH is equal to the negative log of this concentration, or the negative log of 2.8 times 10 to the negative 9, which is 8.55. This demonstrates that our acidic solution has a pOH greater than 7.00. At 25 degrees Celsius, this is always true. Any acidic solution has a pOH greater than 7. Now we can look at a basic solution. In this case, a solution where the hydroxide ion concentration is equal to 4.5 times 10 to the negative 2 molar. As before, the pOH is the negative log of this concentration, or the negative log of 4.5 times 10 to the negative 2, which is equal to 1.35. Notice in this case that our basic solution has a pOH below 7.00. And at 25 degrees Celsius, this will always be true. Any basic solution has pOH less than 7. We are now able to establish a table for classifying acidic, neutral, and basic solutions based on several properties. First, recall from the previous lecture that when dealing with hydronium ion concentration, an acidic solution has a concentration greater than 1 times 10 to the negative 7. A neutral solution has a hydronium ion concentration equal to 1 times 10 to the negative 7, and a basic solution has a hydronium ion concentration less than 1 times 10 to the negative 7. As we just saw, the pH of an acidic solution is less than 7, the pH for a neutral solution is equal to 7, and the pH of a basic solution is greater than 7. From the previous lecture, we saw that the hydroxide ion concentration for an acidic solution is less than 1 times 10 to the negative 7 molar. For a neutral solution, it is equal to 1 times 10 to the negative 7 molar. And for a basic solution, the hydroxide ion concentration is greater than 1 times 10 to the negative 7 molar. And finally, for pOH, the acidic solution has a pOH greater than 7, the neutral solution has a pOH equal to 7, and the basic solution has a pOH less than 7. We're now ready to discuss the relationship between pH and pOH. First, we need to return to the autoionization of water. Recall that this reaction is two water molecules reacting in equilibrium to form a hydronium ion and a hydroxide ion. The ion product constant for this reaction is Kw equal to the concentration of hydronium ion times the concentration of hydroxide ion. The first step is to take the negative log of both sides. This gives the negative log of Kw is equal to the negative log of the product of H3O plus concentration times OH minus concentration. The next step is to use the product rule for logs on the right-hand side. Recall that when we have the logarithm of a product, we can break this up into the sum of two logs. So this gives us the negative log of Kw is equal to the negative log of hydronium ion concentration plus the negative log of hydroxide ion concentration. We can immediately recognize both the pH and the pOH on the right-hand side, but we also have a new p-value on the left-hand side. This new p-value is pKw, and it is equal to pH plus pOH. Recall that at 25 degrees Celsius, the value of Kw is 1.0 times 10 to the negative 14, and therefore the value of pKw is equal to the negative log of this, which is equal to 14.00. Therefore, we have the relationship that the sum of the pH and the pOH at 25 degrees Celsius will always equal to 14. To see how this works, let's return to the example with the solution that has the hydroxide ion concentration equal to 1.2 times 10 to the negative 3 molar. Recall that in order to calculate the pH previously, we had to first find the hydronium ion concentration using the Kw expression. Then we were able to calculate the pH directly. We found that the pH was 11.08. Let's recalculate the pH. This time let's use the relationship between pH and pOH. First, we begin with our definition of pOH, the negative log of the concentration of hydroxide ion. We substitute in the value, giving negative log of 1.2 times 10 to the negative 3, and this gives a pOH value of 2.92. Now we can use the relationship between pH and pOH. Recall that the sum of pH and pOH equals 14.00. This tells us that the pH of this solution will be equal to 14 minus the pOH. Thus, when we substitute in, we find the pH is equal to 14.00 minus 2.92, which is equal to 11.08, the same value we got in the previous example. This concludes the lecture on the pH scale. In this lecture, we learned first that the pH of a solution is a simplified quantity indicating the concentration of hydronium ion in solution. The pOH is a corresponding value, but for the concentration of hydroxide ion. And lastly, the pH and the pOH are tied to one another through the value of pKw, which is equal to 14.00. In the next video, we will see how to apply these ideas to strong acid, strong base systems.